So first of all, good morning. Really nice to have you all here. I hope you had a good break. I really appreciate you being here. It took me a little bit extra energy to get in, but anyway. This is actually the last day of lecture, which is kind of exciting and kind of freaky. The term is just about done. So I want to spend a little extra time today talking about the remaining things happening. So Wednesday, you'll come here to class, and we'll talk about problem set number 6. And definitely bring a printed copy of the hydrogen spectrum lab. This is a lab we're actually going to do in lab, and you'll turn it in before you leave, so there won't be anything to turn in afterwards. It's kind of a fun lab. I was telling Daniel, it's kind of like we'll look at some cool lights and stuff, and so I think it'll be kind of neat, but make sure you bring a printed copy. Make sure you bring your calculator. All right, that would be cool too. And then the last quiz will come out on Wednesday night. It'll be due Friday morning at 9, just like always. And again, next week, we don't have a lecture or lab. But next week, let's talk about what's happening then. All right, so first of all, no lecture or lab. In Chem 221, there's a lecture final and a lab final. Now, normally the lab final would be something you'd actually go to the lab and do, but I can't do that with this class. So what we'll do is we'll have then these 2 finals, and they're both going to be released very early Monday morning, all right? And they'll both be due Wednesday, essentially by midnight via email. So the lecture final will be close to a regular final, a lecture exam we've had. 32 multiple choice questions and a couple of short answer questions over the different chapters. I'm hoping that the multiple choice ones aren't as deep, all right, as the regular lecture exams have been. It's more broad, but of course it does take over all the different chapters, so I know it'll be crazy. The lab final, I'm hoping also will be pretty much review for you, because it's going to have stuff over the different labs we've done. 6 short answer questions. There won't be anything on the hydrogen spectrum lab, because that's the last one, so the other ones are the ones to focus on. So on Wednesday of next week, the lecture final, the lab final, and there is a final exam prep as well that are due. I can help you on the final exam prep. So if you start that up and you have questions on it, then man, let me know. These 2 guys, I'll make sure that you understand what the question is asking, but I won't be able to help you per se on that. I should have your final grades by Friday night of next week. Should be pretty chill. I don't return final exams, it's a regular class or this online class, so just realize that you'll be able to see your grade on it, but I won't actually return it. Do you have any questions on this kind of stuff? Yeah, Kate.
So we're having a final exam prep worksheet that we're turning in with the exam too?
That's right. Yeah, exactly. That's right. If you wanted to print it off and turn it in on Wednesday or something like that, that would be fine. But most people will do it electronically.
Oh,
good. Okay. The important thing on this stuff, like all the stuff in this class, is that if you do have questions, please let me know. I know it's like, end of the term, all right, but it is end of the term, so keep focusing on that, man. The light's coming through the tunnel. We just got to get through a little bit farther and stuff, and then we're good to go. Okay, so what we're going to do today is basically what would be normally like a review for the final, but it is also helpful to you. On Wednesday, when we talk about problem set 6, these kind of questions will be some of the things we'll go over. So ask questions and stuff like that. I'll put up a question, wait a couple of minutes, you can work on it if you'd like to, see if you get the right answer, and we'll talk about what the right answers are, so it should be pretty chill. Again, any questions on anything before? All right, very cool. All right, let's do this. So this first question goes back to the Bohr model of the atom. And it says, how many emission lines are possible considering the 5 quantum levels of hydrogen shown? So it's basically saying that with the first 5 n values, how many emission lines can you get out? So see if you can figure this out. After I wait a couple minutes, I will talk about the answer. So if you want to make a guess just on a piece of paper, awesome. But on the other hand, if you're just like, too early, just hang tight for a little bit and we'll talk about it. All right, so in the Bohr model of the atom, all right, which he kind of pulled out of thin air, there was no basis for anything, he realized that we can model electron behavior using this emission lines, all right, and he called them n values, the principal quantum number n, which is the n quantum number that we've talked about before. And in the Bohr model of the atom, down here at the bottom, not shown, would be the nucleus, the source of the positive attraction, the protons, neutrons, stuff like that. And electrons, which I've written as a dot right here, would start at the n equals 1 level. They call this the ground state. It's the lowest energy. And finally, the y-axis here is an energy axis. And this electron is attracted to the positive proton. It's that positive electron, negative electron attraction thing. Now, an absorbance happens when the little electron gains some energy. All right, sometimes people will draw little arrows. And they sometimes will write h nu, which is the energy of a photon. And if the energy is just right, the electron jumps to a higher level. All right, and this is an example of absorbance. And absorbance is an endothermic process. All right, it takes energy to remove the electron from its cozy place next to the nucleus to a higher barium. And absorbance is a real powerful tool in science, but that's not what we're talking about here. All right. An emission line, which is what this question is all about, is what happens when the electron says, man, I miss home. All right? So it goes from a higher n to a lower n. And in that case then, I'm going to erase all this stuff. In that case, there's actually some energy given off. So while the h nu energy was being absorbed before, now there's actually some energy being given off. And this is emission, and emission is exothermic. And in this section of chapter 6, we're mostly talking about the emission lines, the energy being given off. And the lights overhead right now are actually emission lines coming off, all right? The voltage goes through the light bulb and it absorbs it. And as it relaxes back down to the ground state, some energy is being given off. So all the lights you've ever used are basically emission phenomena, all right? But the first thing I want you to realize is that going from lower to higher is absorbance, endothermic. Going from higher to lower is exothermic, emission. You can see something, all right? Any questions on that? Okay. Now, in this question, it says how many emission lines are possible. So that means higher N to lower N. So I just drew right here the 5 to 1 transition. All right, and that's one of the emission lines that are possible. But there's really no reason why you have to go from 5 to 1. You could go 5 to 2, 5 to 3, or 5 to 4. So in certain books, you'll see like 5 to 2, 5 to 3, 5 to 4. Those would be 4 emission lines right there, 4 possibilities, all right? But there's really no reason why also we had to start at n equals 5. We could have started at n equals 4. And you could have 4 to 1, you could have 4 to 2, and 4 to 3. 4 to 1, 4 to 2, 4 to 3. And there's no reason why I had to start at 5 or 4. You can start at 3, and you could go 3 to 2 and 3 to 1. And finally, you could also start at 2 and go to 2 to 1. So what I've just written up here then are the possible emission lines, all right? 1, 2, 3, 4 from the 5th N level. 5, 6, 7 from the 4. 8, 9 from the 3rd level, and 1 from the 2nd level. So there's a total of 10 emission lines for this particular set of quantum numbers. And in reality, you could have n equals 6, 7, 8, et cetera, but for these 5 and stuff, that's what it is. So a couple of things from this slide. First of all, is that emission lines, high N to low N, exothermic. You'll see the energy, you'll see the light, if it's in our visible spectrum anyway, coming on down. And again, you just literally 5 to 4, 5 to 3, 5 to 2, 5 to 1, that's 4. 4 to 3, 4 to 2, 4 to 1, that's 3 more. 3 to 2, 3 to 1, and 2 to 1 would be then the other ones that are available. Any questions on this? Again, what's so amazing here is that Bohr was able to find this model, all right, which totally came out of left field, all right? There was like no reason for it or anything. But it worked super well. I mean, the accuracy of the predictions are just fantastic. Another thing I'd like to point out here is that in the Bohr model, there was a 1 over n squared part for the energy. And if you look at these n values, they get closer together as you go higher. So the gap from 1 to 2 should be bigger than the gap from 2 to 3, although it doesn't look so right here. But you can see how 3 to 4 is smaller, 4 to 5, and they get tighter as you go up there. And that's something that we'll talk about later. Any questions on this? Yeah. Kate.
I was just going to ask for row 3 there. It goes 4 to 3, 4 to 2, and then 4 to 3 again. So this would be 4 to 1. On the...
Oh, yeah, sorry, that's a typo, man. Absolutely, that should be 4 to 1. Sorry about that, man. So, yeah, yep. Stupid instructor, I'll tell you. I appreciate you all being here after Thanksgiving. My mind is still pretty muddled, and obviously, yeah, I need to look at that a little closer. So, thanks, Gabe. Sorry about that. Other questions? All right. So good old Bohr. And again, this is kind of the stuff we're going to look at in the lab on Wednesday. It's kind of a fun lab. We get to see the laser lights and stuff like that. So as I was telling Daniel, it's kind of like the Van Gogh exhibit, but Chemistry 221 style, and honestly, probably not as immersive. But anyway, I'm babbling on. Let's look at this one. Photons of the highest frequency will be emitted from a transition from level n to some other level n. Now remember that this is emission, emitted, all right? We're looking for highest frequency. And remember what I said, how the n levels get closer together as you get higher. So see if you can use all of this information to find which one of these will have the highest frequency. And you might need to know which one has the highest energy to relate back to the highest frequency. So see if you can figure out which one that is. So this question now, as well as talking about the Bohr model, also is really good about talking about how energy is related to both frequency and, as we'll see here in a little bit, wavelength. And another really important thing, especially from chapter 6, part 1, is we talked about how the energy of a photon, these little pieces of light, if you will, it equals h times nu. And h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Nu here is a Greek symbol. Nu is frequency. And this problem is all about frequency. Now, why that's important is that earlier we talked about how the Bohr model, the y-axis is essentially an energy axis. So we can figure out, for example, which one is the highest energy or the smallest energy. And then we can relate energy back to frequency. And by the way, this is a really fascinating thing that I read about this weekend. This new Omicron Delta variant of this stupid COVID. Anyway, they were going to name it Nu, which is the previous Greek symbol, but they thought that Nu sounded like N-E-W, and that might confuse people, so they didn't want to call it the new variant, even though it's new right here. So anyway, got the Omicron symbol. Anyway, thought it was kind of fascinating. Trying to turn lemons into lemonade. All right, shut up, Michael. I'm talking about. Anyway, this is again an energy axis. All right. So, of the transitions we saw earlier, which one do you think would be the biggest energy? Which one would have the biggest gap between the energy levels? 5 to 1. Well done. And literally, you just look at the sizes of the arrows. That's all you do to figure this out. So yes, okay, well done. The biggest arrow here would be the 5 to 1, all right? Like 5 to 2 is big, but it's not as big as 5 to 2, 5 to 1. So the biggest energy here is going to be the 5 to 1 transition. And energy is proportional to frequency, the nu I was talking about earlier. So biggest energy should have biggest frequency. So we would say the 5 to 1 would be the biggest frequency, all right? So again, this is an energy axis. The biggest arrow would be the 5 to 1 emission line. That would be the biggest energy, and biggest energy means biggest frequency. Good to go. Any questions on that? Cool. All right. Biggest frequency, biggest energy also implies smallest wavelength. All right. Wavelength is the opposite of those two. So in lecture, I was doing the kind of hand waving thing, and I said, biggest energy, biggest frequency, but those both were big means smallest wavelength. Wavelength is the opposite of the other ones. So the biggest energy would be the smallest wavelength as well. And that's kind of important. This problem says we want the longest wavelength based on these different energy levels. So use your understanding here to figure out which of those would be the longest wavelength. And like before, you want to think about how the energy relates to the wavelength. Anyway, think about that for a second. We'll talk about it. So if you look at this equation, we want the longest wavelength, which is like the biggest wavelength. So we want a wavelength here which is big. And when you have something in the bottom in the denominator, then things on the top, for example, like frequency, need to be small, all right? Big things on the bottom imply small things on the top. Remember, h is just a constant, Planck's constant. C is the speed of light, 2.998 times 10 to the 8th meters per second. So both of these are just numbers, all right? You don't have to worry about it. So big wavelength implies small frequency, and small frequency says, aha, we need to have a small energy, all right? So as wavelength gets bigger, frequency gets smaller, and as frequency gets smaller, then the energy gets smaller. So on this list, and remember we want emission lines, we want the smallest energy. Now emission always means, like I said, higher end to lower end. So the first one is not an emission line, all right? 1 to 2, that lower to higher end, that would be an absorbance line, and that's not the same as an emission line. So number 1A is flat out. It could be any of the other ones though, all right? And this is where it's really important to know that in Bohr's model, there's a 1 over n squared dependence on the model. And why that's important here is that means that the n values are getting closer to each other as you go higher up. So the 1 to 2 gap is quite a bit bigger than the 2 to 3. And the 2 to 3 is bigger than 3 to 4. 3 to 4 is bigger than 4 to 5. So that means then for emission, the 5 to 4 line will be the smallest energy, all right? And smallest energy implies smallest frequency, and smallest frequency should mean bigger wavelength. So the 5 to 4 transition is the longest wavelength, all right? It's longest wavelength because wavelength is inversely proportional to frequency. Big wavelength, small frequency, and small frequency, small energy, and the smallest energy, the 5 to 4 transition. Any questions on that? Sweet. So this is the kind of stuff we will do in lab this week, all right? We're looking at emission lines for hydrogen, and it's kind of cool, as you'll see when we do lab. Any questions? All right. Now, I'm going to make you think here a little bit on this one, all right? In this question, hydrogen atoms, all right, they emit visible light when the energy levels end at n equals 2. And I want to stop right there, and this is going to be important for lab. In this hydrogen spectrum, all right, there's definitely n equals 1, n equals 2, n equals 3, 4, 5, 6, etc. The visible lines we're going to see on Wednesday are emission lines, higher end to lower end. And we're going to see 4 lines on Wednesday. One of them's kind of hard to see, but I can see it even with my bad eyes, and you should have no problems. They all end at n equals 2. So one of the lines will be the 3 to 2 transition. One of them will be 4 to 2. One of them will be 5 to 2. And the last one you're going to see will be 6 to 2. So 6 to 2, 5 to 2, 4 to 2, and 3 to 2. These are going to be the visible lines of hydrogen. All right, this is the Bohr model if you look back in the notes. They all end at n equals 2. They start from a higher n and go to a lower n. Questions on that part? Okay, so that's what this first sentence is. The Balmer series of lines are the visible lines of hydrogen. Those are the ones you actually see. And they all have in common that they end at n equals 2. Okay, now here's the interesting part. Well, interesting, all right, remember I'm a chemist. Green light is 4 to 2, all right? So green light is this one right here, all right? Then it says, is the light from 3 to 2, this one right here, expected to be blue or red? Now, when it comes to red and blue, there are definite colors and energies associated with those things. Do any of you know if blue or red would be the higher energy? I heard a whole bunch of comments. Okay, that's a good question. Here's a way to remember this, all right? Infrared is lower energy than visible, and ultraviolet, violet's kind of like blue, ultraviolet is higher energy. So when this question, all right, red would be a lower energy, and blue would be a higher energy. And again, remember this because it comes in handy. Like, I'm always forgetting, but ultraviolet, which is like blue, is higher energy. Like it burns you if you're out in the sun, sunburn, all right? On the other hand, infrared is lower energy. So the question is then, if 4 to 2 is green, which is right in the middle of the spectrum, do you think 3 to 2 would be red or blue? Do you think it would be lower energy or higher energy? Ultramagnetic is just a name of a bad rap band I used to listen to, ultramagnetic MCs. But anyway, it really has nothing to do with this problem. I just need something else there. So see if you can figure out if 3 to 2 will most likely be red or blue. We'll talk about this here in a little bit. Yeah.
You said that red was lower on the spectrum, right?
It's lower in energy mass. Yeah, that's right.
Thank you.
Yeah, no problem. All right, Wes's question was really appropriate because this is basically comparing the energies of these crazy lines again. Now I've drawn here just the parts that we're talking about in this problem, all right? And remember that it really goes 1, 2, 3, 4, 5, 6, et cetera, et cetera. But 4 to 2 is a green line, all right? And the question is, what's the color of 3 to 2, all right? So first of all, is the 3 to 2 transition going to be bigger energy or smaller energy than the 4 to 2 transition? Smaller. Well done. Remember that this y-axis here is an energy axis. And the length of the arrow basically tells you how much energy it is. So 4 to 2 is a bigger arrow than the 3 to 2. That means there's more energy released, if you will, from going 4 to 2 than 3 to 2. So 3 to 2 is a smaller energy transition, all right? And between red and blue, and this is why it's cool that Wes asked, the red is smaller energy, all right? So the red here is going to be the what we would expect the transition color to be. And it's not that we're, Van Gogh experts or something like that, but we know that 4 to 2 is a larger energy than 3 to 2. So 3 to 2, smaller energy, is going to be closer to the red side of the spectrum. If it would have been 5 to 2, a bigger energy, then we would have thought, well, maybe it's closer to blue or something like that. But in this case, it makes sense. It's more likely red. This little part right here for the Balmer lines is going to be important in lab. And if you have nothing else to do with your time, and don't throw tomatoes at me, please. If you look back in the notes on the Balmer series in chapter 6, part 1, there's little lines that 4 to 3, 4 to 2, 3 to 2, 5 to 2, etc. And you can see what their colors are, and those will be helpful in lab. Any questions on? All right. Now, this is another kind of question that will help you on the lab, believe it or not. This is a little bit of a pain, but it is all stuff you can do. And in this question, we have an energy change, a delta E, of 182.3 kilojoules per mole. And you want to calculate the wavelength in nanometers. Now, there's lots of constants going to be used here. You're going to use Planck's constant, you're going to use the speed of light, you're going to use Avogadro's number to get rid of the moles. You're also going to do kilojoules to joules and meters to nanometers. So try this out on your own, see if it'll help. This is definitely going to help for the lab this Wednesday. See what you can do. And again, if you don't want to work on it, that's fine. We'll talk about it here in a little bit too. when chemists use light to enact chemical change, which is photochemistry, they think about light in terms of how many kilojoules of energy they give off per mole of photons. A photon is nothing more than like a small piece of light. You can think about it like an atom, although they're different, obviously. But anyway, in a mole of photons for this light, you get 182.3 kilojoules. And if you look back from the chapter 5 stuff we did, like delta H of products minus delta H reactants, a lot of times those were in this kind of range. So this is what the scientists will do sometimes. But to know the wavelength, what type of light you need, you have to do this kind of back calculation thing, which it's just tedious. It's not hard, but it is kind of tedious. You need to, first of all, turn your kilojoules per mole into joules per photon. So up here on the board, I wrote pH, not little p, little h, by the way, which is joules per photon. And there's 1,000 joules in a kilojoule, so that wipes out the kilojoules. And Avogadro's number says that a mole of anything, including photons, you'd have 6.022 times 10 to the 23rd photons, all right? So if you take this 182.3, multiply by 1,000, divide by Avogadro's number, this number right here, answer A, is what you should get. That's the joules per photon of this light. So if you got this number for joules of photon, fantastic. That's the energy of the photons, which is the first step. Now to get to the wavelength, we talked about earlier how the energy of a transition equals hc over lambda. And h is Planck's constant, which is a number we use a lot in this section. And c is the speed of light, the other number we use a lot in this section. Now, so if you rearrange the equation, then wavelength equals hc over the energy. You've got to use the joule per photon value, all right, the 10 to the minus 19th number. Wavelengths and frequencies as well are always per photon, not per anything else. So anyway, you'll get a wavelength out, and if you did it correctly, answer B is what you should get. So this 6.563 times 10 to the minus 7th, that's the wavelength that you get out of this value. But wavelength, when you use these kind of units, will come out in meters. And the most common use of for visible light is to convert a meter wavelength into nanometers. So the final step, there's 10 to the minus 9 meters per nanometer. This is one of the metric prefixes I asked you to know at the beginning of Chem 221, and it's for this section, okay? But anyway, if you do all of that out, you get answer D. Now here's the work involved. All right, here's 182.3. I divided by Avogadro's and I multiplied by 1,000 to get the joules per photon. I then took the joules per photon, wavelength equals hc over the delta E, and I got 6.563 times 10 to the minus 7th. That's in meters, or 10 to the minus 9 meters per nanometer. So to get it finally into nanometers and stuff, then this is the question. You get 656.3. Questions on this? All right. This is a good, Jonah, did you? Oh, you go. This is a point where there's a good news, bad news, but then good news again. All right. Well, maybe it's bad news, good news, I don't know. Anyway, this is something that happens a lot in this section, all right? They want to convert the light you use, which they use by nanometers, into the energy output, basically the kilojoules per mole. So it's something that's done quite a bit, and these are the steps you do. Again, not hard, but tedious. The good news, this is the good news, is that in the lab this week, the hydrogen spectrum lab, there's kind of a combined equation that converts a kilojoules per mole directly into a wavelength in nanometers, or vice versa. And you can look it up in the lab. I don't know what it is off the top of my head. It's like 1.09 times 10 to the 5th over wavelength equals delta E. It's super handy for this lab. And again, for problem set 6 and or the lab, if you look at that equation, it does save a lot of time, because you don't have to kilojoules to joules to photons and then get it in meters and then convert to nanometers. It like does it all for you, which is super handy if you're doing this kind of work. Any questions on this? So again, this is really good mathematical dexterity, making sure you can use your calculator correctly. If you're not getting any of these answers, please let me know. Dividing by numbers that are really small or really big can create some weirdness if you don't use the E or use parentheses around them. That's the other thing I wanted to highlight here. Any questions? All right. This is the other kind of weird equation from this section. And this is an example of the de Broglie wave equation. Now, wavelength is something that's definitely associated with standing waves, which are basically the types of waves we're looking at with red light, ultraviolet, et cetera, et cetera. But what de Broglie figured out is that actually matter can exhibit waves as well. And so this question is essentially asking for a wavelength for an object. And again, I want to point out how weird that is because, I've had a lot of caffeine this morning, but I'm hoping you don't see me kind of have wavelengths, all right, as I move back and forth. And I've been drinking alcohol either for that matter. But people, objects, we don't expect to have waves associated with them. But in reality, when you get down to this super small area, sometimes they do. So anyway, in this question, see if you can find the wavelength for this electron. Now, the mass in chemistry is almost always grams, but this is one time where you have to use kilograms for the mass. So see if you can figure this out. I'll put a few notes up here on what all these pieces might help you with. See if you can get it. de Broglie's wavelength equation looks like this. It's wavelength, which is the lambda symbol, equals h over mv. Now, h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. M is the mass. And again, in this kind of equation, you have to use kilograms, not just grams. So that's the only kind of the main weird thing about this one. Notice that this one was given to you in grams, so we'll do a conversion from grams to kilograms before we plug it in. V here is not frequency, it's a true V for like velocity in physics, it's the speed of the piece and stuff. And in this problem, the electron is traveling at 1.20 times 10 to the 8 meters per second. So what we'll do, Planck's constant on top, the mass will be this thing in kilograms, which means we essentially divide by 1,000. So we'll use a 10 to the minus 31 there. And the speed is literally this number right here. Now, we have all what's called SI units in this problem, all right? H is joule seconds. Those are all HSI. Kilogram is the mass, which is the official thing. Speed is meters per second. So the wavelength that comes out is going to be meters, all right? It's not nanometers. And we'll see here at the end, we also need to do a meter to nanometer conversion, again, all right, 10 to the minus 9 meters per nanometers, in order to make sense of the answers that are given right here. So if you got answer D, outstanding. The first part right here, wavelength equals h divided by mv. Here's the mass in kilograms, so 10 to the minus 31 instead of 10 to the minus 28. And the answer you should get out is 6.06 times 10 to the minus 12. And that truly is the meters. So if you put down this number, you're super close, but it's not 10 to the minus 3, it's 10 to the minus 12. But if you convert then to nanometers, I use 10 to the positive 9 nanometers per meter. You could also have 1 nanometer per 10 to the minus 9 meters. Either way, you should get out to be 6.06 times 10 to the minus 30 nanometers. This wavelength is actually a wavelength which you can observe, all right? Like the wavelength of me walking back and forth is nothing. We couldn't measure it. It's way too small for the technology we have. But when it gets down to super small things traveling pretty fast, then oftentimes we can measure the wavelengths. Electrons are great at this, so they behave both as waves and particles. Makes them kind of weird. Anyway, questions on any of this? Yeah, Kate.
So you took the wavelength at the bottom with meters, and did you multiply that 10 to the power 9?
Yeah, you can either multiply by 10 to the 9th, or you can divide by 10 to the minus 9, then you should get the same answer. Like a 10 to the minus 9 on the bottom is like a 10 to the positive 9. So the official way, it's 1 nanometer on top, 10 to the minus 9 meters per bottom. But you can see that my old school way of thinking here slipped in, to be honest. I'm used to thinking about it as 10 to the 9th nanometers per meter. Either way is cool. Good. Freedom to choose, Pepsi or Coke, whatever. Yeah. Other questions? All right, this is a good place to take a break. It's about 9:57, so 10:02-ish, something like that. We'll come back here.